Hello everyone, we are back today with part 2 of our tutorial series exploring Haxe and OpenFL. I think Haxe is about 16 years old now, and you know it's funny? I often tell people that Haxe is probably the best programming language they've never heard of, and sadly it's true. Though considering what Haxe is capable of and how long it's been around, I really think it's earned a much greater place in the overall development landscape than it's currently achieved, although I do see a lot more companies using Haxe today, which is a pretty awesome thing. If you've wandered onto this video or the tutorial series, then you probably already have more than a little interest in Haxe and presumably OpenFL, whether you just want to build a great new application for the web or you are trying to mod an open source game like Friday Night Funkin', this is definitely the right place to get started. In this video, we are going to take a little deeper dive into Haxe, leaving off from the introduction in the first video, part 1. If you're just joining now and you want a briefer introduction to Haxe, go ahead and check out the first few minutes of that video and get up to speed. Well, what is Haxe? Haxe is a modern, high-level, strictly typed programming language that follows basic object-oriented principles and ECMA-based syntax with a focus on being general purpose. To this end, Haxe is coupled with a robust cross-compiler written in OCaml that lets us write and deploy our code to multiple popular languages or VM bytecode seamlessly. Most of all, its simplistic design is easy to use and powerful enough to get the job done. So yeah, it's a high-level object-oriented programming language, but what can it do? To be blunt, Haxe is kind of like a Swiss Army knife. I can go on and on for hours about all of Haxe's features and what it's capable of, but I'd probably have an easier time trying to explain what Haxe can't do because the list is pretty short. In this video segment, however, we're just going to go over some of the important features. I think it's important to explore. If you really want to go down the rabbit hole, check out the learning resources on haxe.org because most of this information can be found there. So the first thing we're going to look at is abstract types. Per the haxe.org definition, an abstract type is a type which is actually a different type at runtime. In other words, it's a compile time feature that gives us the ability to augment the behavior of another type. Let's go ahead and create an example. We already have a blank project set up with all the boilerplate, so let's just go straight to creating our first abstract. In these instructions, we're going to be building the hash link for short compile times. Feel free to follow along using any target you prefer. So the first thing we want to do is create a new Haxe file. The keyword abstract allows us to declare an abstract type. The name of our abstract is going to be called text. Text is going to augment the behavior of string. String, the underlying type, goes in the parentheses. The fields, of course, are enclosed in curly braces. So far it looks like a regular class, and like a class, it also has a constructor. For our constructor parameter, we're going to accept string as type string. The semantics here are quite similar, however an abstract cannot have physical properties. For the most part though, abstracts can be used exactly like classes. However, abstracts serve a different purpose. For example, an abstract may allow you to set its internal value using this, as in THIS. However, this can only be done in the constructor or in inline methods. That's okay, there are plenty of uses for classical member functions. Let's go ahead and augment some string behaviors. First, when we instantiate a new text abstract, we will set its internal value to the parameter we passed in the constructor. Next, let's create an example of an inline method. Our method is going to be called insert, and we'll accept a string and return a string. Let's also accept an index Alright, so what this function is intended to do is modify a string in place by inserting another string at a particular index. In our return, we'll write this equals this dot substring 0 index plus string plus this dot substring index this dot length. So not only will our new function modify the string in place, it'll also return the string. So let's go try out our new string behavior. First, let's save our class. Let's go to our main class. Create the variable text, type text equals new text. Let's say hello world. And let's just make sure our abstract is behaving correctly and trace out text. Alright, and there's our trace statement. So our abstract is working correctly. Now let's try and use our new method. Text.insert. The string bright. An index of 6. Let's go ahead and add a space at the end of that and run our project again. And now it should say hello bright world. And there you go. So let's go back to our text abstract. Now, we can't set the internal value in a regular method, but we can access it and do other things. So let's create another method called split at, and we'll accept the parameter index, integer. We're going to return an array of string. And we're going to return this dot substring 0 to index and this dot substring index to this dot length. And basically what this method does is splits a string into two array items at a certain index. Let's go test it out. Save. We'll split it at the index of 6. And we'll trace out the very first iteration. Which should be hello. Let's go ahead and test it. And there's our trace statement. So if you don't quite understand how this works right here, don't worry. We'll cover it later. Alright, and so with that, we've tackled the basics of abstract types. Now, this isn't all that abstracts have to offer, but it is enough to get a general understanding of how they work. When used correctly, abstracts can be a powerful tool in your development process. This tutorial series is primarily devoted to OpenFL, so we won't go into every nook and cranny here. Now let's take a quick look at anonymous structures and build on our previous example. Information and data can be easily utilized by anonymous structures, reducing the need for small interfaces or data classes. Properties can be created using key value pairs separated by a comma, or even by using JSON syntax with quotations. This is a simple, convenient, yet powerful feature for many use cases. Let's go try it out and put our abstract and some other arbitrary data into an anonymous structure. Let's go back to our main class and create a new variable called struct. Equals curly brackets. Now let's add an arbitrary value key pair. We'll call it number. $100. Let's add a comma to separate our next value key pair, which will be text. Text. And there we have our anonymous structure. Let's go ahead and try and trace some properties out of it. Trace struct.text and struct.number. Let's get rid of our last trace statement. Go ahead and run it. Let's look at our debug console. And there we have our trace statement. This allows you to group data without explicitly creating a type. A structure is always enclosed in curly braces, has a comma separated list of key value pairs, and a colon separating the key, which must be a valid identifier. The value can be any expression. Structures may be nested and complex and cannot subvert the compiler's typing system, ensuring that the program will not compile if the fields cannot be accessed. As I mentioned earlier, JSON syntax can be used like this. This will compile and give us the same result as before. Alright, so you should have a pretty good understanding of anonymous structures by now, so let's move on to something else. Next, we're going to look at array comprehension. Array comprehension allows you to declare an array containing a loop such as a for while loop to enable streamlined population of arrays. For the next part, I'm going to assume you already understand how Haxe loops work, but if you don't, now might be a good time to check out some of the documentation for some of the simpler things at haxe.org. Let's continue building on our ongoing example and try out an array comprehension by using a loop to split all of our characters in our text variable and populate them into an array using array comprehension. Let's go back to our main class and create a reference. Go ahead and delete that. Let's go ahead and create a reference to an array called chars. Okay. Array of string equals some brackets, Now we're going to utilize the array comprehension. Let's go ahead and write in our for loop for, say, I in 0 to, let's cast our text into a string. Dot length. That's already encapsulated, so let's pop over here and write cast text string dot char at I. Let's go ahead and trace out our array. And go ahead and run it. Let's take a look at our debug console. And here you see our array containing all of our characters. And that's pretty much it. As an object-oriented programming language, Haxe has your typical classes, interfaces, and inheritance, similarly to languages like Java. Object-oriented programming is a big enough topic alone that it would require its own entire video just to go through, so we won't do that here. And there are probably many videos, tutorials, and other resources about object-oriented programming out there that you can educate yourself with, and it's not something that's Haxe-specific if you are unfamiliar. I may make a video outside of this tutorial series covering this as a fundamental, though. You should probably learn what object-oriented programming is before continuing with the tutorial series. For now, we're just going to go ahead and skip into conditional compilation. Compiler flags were one of the most exciting features for me when I first tried Haxe. Conditional compilation is an extremely valuable tool for debugging, managing source code for different build targets, and yeah, lots of other stuff. The conditional compilation system allows you to feed the compiler instructions in order to control which code within your source to build and which code to omit based on a configurable set of conditions called flags. For example, if you could include operating system specific code and only include the code for that system when you build your source. This alone empowers you to support multiple platforms from a single code base. OpenFL takes advantage of this conditional compilation to do just that, and a bunch more. So let's go ahead and dive in and take a look at exactly just what this means and how to use it in the most simplest way. Okay, so in this example, we're not going to get rid of our last trace statement. Instead, we're going to write a conditional compilation block around it so that we can control whether it traces out or not, depending on whether we are building to hash link. So let's go ahead and type if HL for hash link, which is one of the definition set, end to enclose our condition here. Let's go ahead and test it. And of course it should trace out. Now if we don't want this code to be included when we build for hash link, we've added our not operator. So we can go ahead and test that again, and it should trace nothing. And we have nothing. So let's go ahead and open up our project XML, and we're going to add a definition of our own. Let's type in Haxe def name equals trace on, and then just close up the XML there. Go ahead and save it. Let's go back to our main class. Alright, now we're going to do something a little bit different. we are going to add a AND operator, and we're going to include the definition we just created in our project XML. Trace on, and of course we know this should probably not compile, so or rather that the trace statement shouldn't be included because we are building to hash links. So we're just going to go ahead and get rid of the not operator to test it, and let's go ahead and run it. And there's our trace statement. Now let's go ahead and remove the hash link condition and the AND operator. And of course, if we run this, we still get our array to string trace here. Alright, and now let's go back into our project XML, and let's just go ahead and comment this out. And run it again. We should not see our trace statement. And there we go, no trace statement, because we no longer have our define here. And the code here on line 21 was never included in the build. So yeah, that is basically conditional compilation. I guess you can probably use it in a few more complex ways, but you should have a pretty basic understanding now, and I guess we can move on. Haxe features support for enum types, which you may or may not be familiar with already. They're a pretty simple but incredibly useful way of describing data structures and controlling switch statements, for instance. Let's go ahead and create our own simple enum in the ongoing example source. First, let's go and create a new Haxe file. Package. The keyword enum indicates that we're declaring an enum. Level is going to be the name of our enum. Once again, this can be anything conforming to the rules for type identifiers, and if you don't understand what this means, you should probably go ahead and search for Haxe type identifiers. Next, nested within the curly braces are going to be the enum constructors. As you can see, we will have one called low, medium, high, and range. Now notice the last one here. Range is different from the other three as it expects two arguments, min, an integer, and max, an integer. In a minute you'll understand how this works and what we can do with it. Now let's go ahead and save it. Level.hx. And let's go back to our main class here, and we're just going to leave that trace statement alone. And let's write up a switch statement. The switch is going to be level. Let's go ahead and create our braces. Let's create a reference for level. It's going to be the type of level equals, let's say, get level, And we will go ahead and just create that method really quick. And it's going to return a level enum. So let's go ahead and create our brackets. And let's say it returns level dot range 0, 100. Alright, let's go back to our switch statement and finish that up. Let's write case low trace is low case medium trace is medium case high trace is high case range min max trace min max. Okay, and it should trace out as 0, 100. Let's go ahead and test it out. And there's our trace statement. Since this isn't a very good use case, let's try to do something a little more gainfully practical with our getLevel method. Let's go ahead and add the local vars min max. Now let's create a loop. Let's say I in 0 to 10. Let's go ahead and use the math standard library and grab a random float. Let's say 200 minus 100. Alright, so if you've been following along so far, you'll know that this line of code will create an array with 10 random floats between the range of -100 to 100. So now at least we have some kind of data set, even though it's random and pretty useless. But maybe now we can do something with our enum that is a little more meaningful. Now let's add one more local var. We'll call it total. Alright, now that we have everything I think we need, let's go ahead and create another loop. Now, I understand we could have populated the random array and done the processing loop all at once, but for the sake of simplicity and making it easy to understand, I'm just going to go ahead and separate it. So let's type in for j in 0 to rand array.length let's do min equals math dot min rand r j and max equals math dot max rand r j. I'm pretty much making up this use case as I go, so let me just flesh out some more logic here. And we'll go ahead and explain it. Let's change this. If j equals 0, max equals min equals rand r 0, let's see if total is more than 100 and total is less than 125. Return low. Else, if total is more than 125 and total is less than 150, less than equal. Return medium. Else, if total is more than 150 and total is less than or equal to 175, return high. Else, return level dot range min max. Oh, and we're going to need to add std dot int to convert these floats into integers. Okay, so let's get an overview of what we did here. So the getLevel method basically measures the volatility of the math random number generator using Enums. So basically, if the difference between the minimum and maximum random number is, if it's over 100 and less than 125, we return a level of low, If it's between 125 and 150, we return medium. If it's between 150 and 175, we return high. And for any other value, we simply return the level range with the min and max integer. Alright, let's build it a few times and see what happens. Well, it seems I've forgotten a semicolon right here. And let's try it again. Alright. Is high. There's our integers. Is medium. Is high. And our integers again. Alright, I guess we get the point. So this basically covers enums usage. I know my example wasn't really that great. It's not very practical. I was just trying to come up with something that would give you a rough idea of how enums work, and I think we accomplished that here, so let's move on. Next, we're going to take a brief look at inline functions. Now, the inline keyword allows function bodies to be directly inserted in place of calls to them. What this basically means is that the compiler can directly substitute the body of a function in place of a call to that function, thereby saving you the overhead of an extra function call. In several cases, using inlines can greatly speed up your code execution. However, you should probably use them pretty judiciously because there are definitely situations in which they can work against you. Variables can also be inline using the inline keyword, and as some of you may have already noticed, we do not actually have a constant in Haxe, although we actually kind of do because that's exactly what an inline variable is. Variable inlining can only be done statically and cannot be changed at runtime. It's also important to know that since Haxe 4, using the final keyword is more appropriate instead of inline for our static variables. The final keyword didn't exist prior to Haxe 4, and there's no telling if and when they'll depreciate the continued usage of the inline keyword for that. Okay, so we're only going to make a quick example here since there's not really much to explore, although if you have some more questions afterwards, I would consider reading a little bit about inlines on the web. Okay, so let's go ahead and create a new inline function. I guess I could inline this function here, but this isn't a very good candidate for an inline function. Let's go ahead and type static public function get string. Pretty simple. Okay, it's going to return a string. Return Haxe plus is plus grade. Yeah, pretty corny, right? Alright. Let's go ahead and trace get string. And build. Alright. And there's our string. Now, there's nothing that fancy going on here, but let's take a look at what Haxe is actually doing. When Haxe compiles your code, it's actually looking something like this. So you're not actually making a function call, which will reduce execution time in this situation. Now let's try using an inline function in another way. You remember when I said that this function here wasn't a very good candidate for inline? Well, let's do it anyway. All I need to do is type in the inline keyword and run it. As expected, this doesn't work for many reasons, not least of which is that our function doesn't return a final, and not because we can't use it this way. So let's go ahead and try something different. Remove the static. Remove this. Let's trace keyword inline. Remove this. Build. And as you can see, our function worked just as it did before. Function calls can be inline this way, but constructors can as well. The last thing I want to do now before we move on is create a static inline variable. We're just going to go ahead and type public static inline var my static var string equals my static var. Alright, let's go ahead and trace that out somewhere down here. Go ahead and build it. And there we go. Alright, moving on. Next, we find ourselves on the topic of iterators. You might already be able to guess what these are, unless you're already familiar. But to put it simply, an iterator allows us to iterate over iterable data types and structures. This is exposed in the API by the iterator hasNext and next methods. Furthermore, any iterable type may be iterated over by utilizing a for loop. We're going to look at two ways we can iterate over some iterable data, and it just so happens that we already have something that we can iterate over, the character array we created earlier. Let's go check it out. The first method we're going to look at includes using a for loop. Using our chars array iterator, we're going to trace out every character in the array. So let's go ahead and type for char in chars curly braces trace char. And let's run it. And as you can see, it traced out every character in the array. That's just one example of iterating over an iterable data type like an array. Now I'm going to show you another method using a while loop. Let's go ahead and comment out this trace. On the next few lines, let's type while char iterator dot hasNext curly braces trace char iterator dot next, and we'll just go ahead and create the char iterator variable. chars.iterator, and let's go ahead and run it. And just like before, it's traced out every character from the array. Next, we're going to explore local functions and arrow syntax. Arrow syntax is a popular ES6 feature that finally made its way into Haxe in version 4. Functions in Haxe are not limited to class fields and can also be included within expressions as well. In the next example, we are going to look at using local functions and arrow syntax. First, let's go ahead and comment out our last trace statement. This way we don't clog up our debug console. Now in the next few lines, let's create our local function. In the body of our function, let's type trace function A. Don't forget our semicolon. Oh, and let's break this while loop so it doesn't make our application hang. Now let's go ahead and test it. As you can see, our local function has been declared, but it hasn't been called. So let's go ahead and call it. And run it again. And there's our trace statement. Now let's do the same thing with arrow syntax. Down here, let's type var function b equals parentheses arrow curly braces. Don't forget our semicolon. Let's trace out function b. Go down here, let's call our function. Let's run it once more. And there you have it. The arrow syntax gives us a short, convenient method of declaring a function, although you cannot set a return type. This is as far as we're going to go in this example, so let's move on. Compiler metadata is a very complex Haxe feature that has far too much depth to go over everything here. At some point I will definitely create a video dedicated to things like metadata and macros, but in this video we are only going to get a very small taste of what you can actually do with metadata. And if you just can't wait for me to go into it deeper in the future, I highly suggest that you read about it and view the list of metadata types on the web at haxe.org. Metadata can be added to fields, classes, or expressions to communicate information to the compiler macros or runtime classes, and in our short example I'm going to show you a very useful metadata that can be used to circumvent private access limits. This is going to be pretty helpful when working with library internals, so let's see how it works. For this example, I've already gone ahead and created a supplemental class with a private property that we are going to try and access with the private access metadata. Let's go ahead and take a look at the private access example class. Our class has no constructor, but it does contain one private static variable called hidden property, which is a string that reads, here's our private property value. By default, private properties and methods are walled off from external access. However, by using metadata, we can force the compiler to give us access, which, under normal circumstances, the compiler would throw an error. Let's see what happens when we try to trace out the hidden property field without the metadata. Trace private access example dot hidden property. Let's go ahead and build. The compiler throws an error. Line 63, cannot access private field hidden property. So now, if we just add at private access and try it again, the compiler doesn't complain and our application builds. But most of all, here's our trace statement. This is just one of the many ways to use metadata. Other notable things you can do include accessing entire classes with private access, operator overloading, array access, embedding files, and a ton of other stuff. And with that, I think we're moving on. Next on our list is a small feature called string interpolation. There's not a whole lot to say about this one, but it is a very useful feature. This allows us to access variables enclosed in strings declared with single quotations when each reference is prefixed with a $sign. Let's take a quick peek at what this looks like before we move on to the next topic. Let's start out by declaring a new variable. It's going to be an integer. Let's call it number. Equals 7358 semicolon trace displaying the number. Let's go ahead and build it. Displaying the number 7,358. So now what if we wanted to access a nested property? What does that look like? Well, let's see. Let's go ahead and add a public static var to our old private access example class. Equals 9867. Let's go ahead and save it. Go back to our main class. Let's see what happens when we try to use a nested property. Let's go ahead and try it. So it didn't throw an error, but it didn't trace out our value either. Fortunately, there is a way. All we need to do is add some curly braces. And that's it. Let's try it again. This time we should see our number. Displaying the number 9867. There you go. There's really nothing more to be said about string interpolation. So let's wrap things up and move to the end of the list. As we make our way down to the end of the list, we find ourselves staring at type parameters. This is actually something we encountered earlier in our example when dealing with arrays, and I promised I'd come back to it. Type parameters are allowed to be passed on class, enum, enum constructor, function, and structure. They are bound either upon instantiation or invocation in the case of function. The array is a good example of a type parameter usage. When an instance of array is created, its type parameter can be bound to any type, but only one at a time. To put it in simpler terms, at least in the case of an array, a type parameter is expected and should be consistent with the type of objects that it will contain. An array cannot hold objects of different static types at the same time, with the exception that dynamic is passed in the array's type parameter. This is yet another one of those topics that definitely deserve more than just a few minutes of screen time, and I wish I could go into every detail of every feature, but it's a little extracurricular to the primary substance of this tutorial series, which is ultimately intended to focus more heavily on OpenFL software app and game development rather than Haxe basics or beginner level content. Even in this video, we really haven't even barely scratched the surface of all the core Haxe stuff, and there's really just a lot of different things that we didn't even get to mention, like Haxe steps, static extensions, partial function application, macros, and so much other stuff. So, you know, if you feel like you just haven't gotten to know Haxe as much as you feel you should, then I really implore you to go out there and just read all the resources and materials and documentation that you can find. There's a lot of stuff available. I've plugged the Haxe.org website like 7 times in this video already. Go learn Haxe. And finally, where does Haxe go? It'd be easier just to say it goes everywhere, and that would only be a slight exaggeration. Because honestly, between JavaScript, JVM, and CPP alone, where can it go? Developers have created software for things like BlackBerry and TiVo, Raspberry Pi, smartwatches, TVs, consoles, automobiles, mobile phones, tablets, computers, Arduino, you name it, the list goes on and on. Haxe includes a standard library that is generally supported on every target, and is accompanied by target-specific API offering all the tools that you need to develop for almost every platform imaginable. To answer the question, Haxe will go wherever you want it to go, wherever you need it to go, and wherever you'll take it. And why should we use Haxe? So at the risk of sounding like a broken record, I guess I'd have to ask, why shouldn't we use Haxe? Haxe is lightweight, open source, full stack, cross-compiled, has modern features, is extremely versatile, very familiar, easy to learn, convenient, works on your favorite IDE, offers a blazing fast virtual machine in the form of HashLink, and is backed by popular renowned libraries like OpenFL, Flixel, Feathers UI, Armory, and Ka, plus the incredibly brilliant minds over at the Haxe Foundation. And in the last 16 years, Haxe has definitely matured into something I think is pretty special, and I would bet that there's just a little bit of something out there for everybody if they gave it a try. Why should we use Haxe? Imagine using the same high-level programming language to handle tasks you might have traditionally used multiple technologies for, developing your front end and your back end with the same familiar tool set. Imagine having a team of diversely skilled programmers with the skills from different target-specific backgrounds working together to build a code base unified by a boundless language. Imagine having the ability to develop with native code without understanding a bit of C. This is the power of Haxe. Why should we use Haxe? Probably because it's the best programming language you've never heard of. So we've made it into just about the 1 hour mark in this video, and if you made it all the way through with me, then kudos to those of you that did. I'm sure at least some of you are wondering, where do we go from here? Well, in our next video we will be taking a similar stroll through OpenFL, and then hopefully in a few weeks we will start learning how to build some pretty cool stuff as we look into actual game and app development. I've got a ton of content planned for this tutorial series, and we're just getting started. If you want to follow along and support what I do while learning how to build cross-platform applications, for now the greatest thing you can do is just like and subscribe. Make sure you check out the description for a link to the source materials from our example today. On that note, thanks for watching, and we'll see you next time.